All right. Thanks. So this will be the last talk in my series of talks, and I want to now discuss more general Berkovich curves. I had been focusing for the most part on the projective line and also on the space M of Z, which was our cute toy example for illustrating various things. And now I want to work on Berkovich curves. And it's convenient to have waited to this point because Brian has now defined the category of Berkovich analytic spaces. And we can assume a little bit more than I've been assuming in the previous lectures. And so this is necessary when working on more general curves. So what I want to do is describe how to generalize some of the constructions and visualization techniques that we use to sort of understand the Berkovich projective line in the context of curves of higher genus. Now, when I say Berkovich curves here, as I'll write down in a moment, I'm thinking of the analytification of a smooth, proper, irreducible curve over an algebraically closed field. So it's a rather restrictive notion of a curve, but one that's sort of analogous to the concept of a compact Riemann surface. And we're trying to do the analogous p-adic theory that would be parallel to our understanding of the classical complex analytic space associated to a Riemann surface. But in fact, Thuillier, in his PhD thesis, where entitled something like Potential Theory on Berkovich Curves, but in French, was he actually developed a more general version of this theory. There's no restriction that the base field be algebraically closed. There's no restriction that the curves be proper, etc. So there's definitely a more general theory than this, but I'd like to stick to a simplified case. Even though it's simplified, I will assume more about rigid analysis and Berkovich's theory than I did previously. Okay, so to review our notation, this field K will be algebraically closed and complete, and the valuation is non-trivial. R is the valuation ring of K, and K tilde will denote the residue field. And X will be a smooth, proper, and irreducible algebraic curve over K with associated rigid analytic space X ridge and associated Berkovich K analytic space X Berk. So so as Brian just mentioned, often this would be written Xn, but I will write it as X lower Berk. Okay, so the key to understanding the topological structure of Berkovich curves is the semi-stable reduction theorem. So I want to say briefly something about semi-stable models. Now in general, one should work here with admissible formal models in the sense of Raynaud, but I will work with models in the category of schemes, possibly for simplicity, depending on your point of view. So a semi-stable model for my curve X is a proper flat scheme X over R whose generic fiber is my given curve and whose special fiber is a semi-stable curve over the residue field. And I'll remind you that a semi-stable curve is one which is reduced and the only singularities are ordinary double points. So we just have some components crossing transversely with ordinary double point singularities. And the semi-stable reduction theorem tells you that every curve that I'm considering has a semi-stable model. So in higher dimensions, there's a serious problem in visualizing Berkovich spaces, partly due to the lack of suitable analogs of this theorem. But in dimension 1, one knows that every curve admits a nice model, which one can build a model of the Berkovich space from in a way that I will describe. And so I will choose without comment, for the most part, some semi-stable model, script X, and I will let Z denote its special fiber, so we don't have too many tildes floating around. And well, certain constructions I make might appear that they depend on the choice of the model, and I suppose some of them might, but many of the constructions will actually be independent of this choice, but that may not be obvious, but you can just imagine having fixed some model, but in fact the Berkovich space knows about the system of all semi-stable models, as I'll describe, and so in fact this choice is not so important. And I will denote by pi the reduction map from, remember k is algebraically closed, so from the k points of x to the k tilde points of z, which we will later promote to a reduction map from the Berkovich space associated to x to the scheme associated to z, including the non-closed points of z. So formal fibers, this is some terminology from rigid geometry. If I have a closed point of the special fiber, I'm going to write x of z, or pi inverse of z, for the formal fiber of x over z. So this is just all things that reduce under this reduction map to z. And, oh, by the way, this I was supposed to say that this reduction map depends on my choice of a model. So that's, in order to have such a reduction map, I need to fix a model. So all of these things here depend on this choice. So the formal fiber x of z carries the structure of a rigid analytic space in a natural way. And A of alpha minus will denote the standard open annulus of height alpha. So in the language of rigid geometry, it's this spectrum of k t alpha t inverse. So it's one of these Laurent domains. And the open, oh, I'm sorry. Oh, yeah. I had a closed annulus and an open annulus, and I deleted one of them and I was supposed to delete this. So this was describing the closed annulus of height alpha, and then this is sort of the formal fiber over the singular point of that. So just ignore, I can't do what Brian did and cross it out with a pen. So, and I don't think I can quickly edit the LaTeX file. So let me just tell you to ignore that right there. Theoretically, this is correct here. You're supposed to think of this as the points whose absolute value is strictly between alpha and 1. Thanks. So theorem of Bosch and Lütke-Bomert is that if I have a point in the closed point in the special fiber, then if it's a non-singular point, then the formal fiber is analytically isomorphic to the open unit disk, analytically isomorphic in the category of rigid analytic spaces over K. So for smooth points in the reduction, the set of all things that reduce to that point just looks like an open disk. And if you have an ordinary double point, and remember, I'm assuming the only singularities are of these two types, then x of z, the formal fiber is isomorphic to a standard open annulus of height alpha. And actually, this number alpha is uniquely determined. So this is a very useful result, as we'll see. And actually, we've seen this kind of thing in Jeremy Teitelbaum's talk, the open annuli that he's seeing in terms of this reduction map to the Bruhat-Titz tree is closely related to this fact here. The appearance of the open annuli and disks is the same phenomenon. So this is nice because it says that we can kind of fiber, well, maybe that's the wrong word. We can look at our space as mapping to this algebraic curve Z over the residue field, and the fibers are either open disks or open annuli, which are spaces that we understand. So we should somehow, in a sense, be able to glue open annuli and open disks together to get our Berkovich space, except gluing along what? These are all disjoint sets, so that's not how one should define the gluing procedure. So the gluing procedure arises from the dual graph, as I'll explain. So if Z1 through ZT are the irreducible components of my special fiber, Now, for simplicity, I want to assume that these components don't intersect themselves. But this is, I mean, either you can reduce to this case easily, or you can treat the more general case without much more difficulty. But just for simplicity, so I don't have to add extra notation for the normalization of these components, let me assume that these components are themselves smooth. And the dual graph, gamma z, I can think of it either as attached to the special fiber or to the model that I chose in order to get this special fiber. It's the graph whose vertices correspond to the irreducible components and whose edges correspond to intersections between those components. So the edges of the graph correspond to the singular points of z. And in fact, we've seen this in Jeremy Teitelbaum's talk when he was describing Shimura curves and uniformization, p-adic uniformization theory. This is the same dual graph that appeared there. And as we'll see, this graph can be naturally endowed with the structure of a metrized graph. So the content of this is that there's a natural metric. There's a natural way to measure the length of an edge here. And remember, what is an edge? I mean, I'll just say basically what it is now, and then I'll explain it a little more. An edge corresponds to a singular point on the special fiber. And if we want to attach a length to it, well, we've already seen a number, alpha, that's intrinsically associated to this, right? The formal fiber over this singular point is an open annulus with, and the log, let's see, alpha is between 0 and 1. So I guess the negative log of alpha is going to be a positive real number, which we'll call the modulus of that annulus by analogy with complex analysis. And the modulus minus log of alpha is actually a conformal invariant and does not depend on any choices. And this will be used to give that edge a definite length. And so in this way, we will be able to endow gamma with the structure of a metrized graph. And second, there is a natural inclusion map of this metrized graph into the Berkovich space, and a natural retraction map of the entire Berkovich space onto this graph. And so in this way, we're going to get this arboretum structure that I just described in the previous lecture, where we have this compatible family of inclusion maps on the one hand of metrized graphs into one another, and also a compatible family of retraction maps between metrized graphs. So this is slightly less clear, for example, why this reduction graph actually embeds into the Berkovich space. So I'll try to explain that next. Here's an example to keep in mind. I've already shown this picture once, possibly on a different scale. I can't remember. This looks very big. So this would be, for a Tate-elliptic curve, you can view this circle as topologically being the dual graph of the special fiber of some appropriate semi-stable model for an elliptic curve with multiplicative reduction. And then, in fact, this whole circle embeds homeomorphically into the Berkovich space, and then we have all these trees hanging off. And I'll explain now where the structure comes from. But roughly speaking, all these extra points here they actually are coming from other models. You just blow up lots of points on the special fiber, and you introduce new P1s, and you keep blowing up in different ways, and you get more and more projective lines. And when you take the dual graph, this corresponds, on the level of dual graphs, you're adding trees. So you start with some nice skeleton like this circle, and when you start blowing up points on the special fiber, you add more and more trees to your space. And the Berkovich space is obtained by some kind of limiting process over all blow-ups, or equivalently over all semi-stable models. So that's something I'll make precise in a minute. So you can obtain this rigid space associated to X by in the following way. And I wasn't sure it was worth introducing all this new notation, but I'll give it a shot. So for each component Zi, this is described, by the way, in this book by Fresnel and van der Put, but without many proofs. But they use this notation that I'm using here. So Zi star is the non-singular affine curve obtained by removing all the double points of Z which lie on this component Zi. I'll show a picture in a minute. And the formal fiber, or the pi inverse of this, pi inverse of Zi star is actually an aphanoid. And for each singular point P, which lies on, say, the two components Zi and Zj, you can let Z sub P be the Zi star union the Zj star union this point P, and let xp be the pi inverse of that thing. And this is, again, an aphanoid. I'm just going to try to describe how you can visualize a curve by gluing together aphanoids that somehow depend on just on the reduction graph, or are sort of dictated to you by the reduction graph. So what you're doing is you're gluing the aphanoids x sub p. These are parametrized by the singular points on the special fiber along these aphanoid subsets xi star. Yes? So the question is, if I have just two P1s crossing at one point, then ZP is the whole thing, right? Yeah, so maybe I need a stable model rather than a semi-stable model or something along those lines. So, okay, sorry. So, yeah, to make it, if I want an aphanoid space, I could just remove one point. And, okay, so yes, this. Right, so if we apply this Berkovich analytification functor that Brian described, then from this data of gluing rigid space, aphanoid spaces together along aphanoid intersections, we get a, well, I wrote locally ring space, but as you see, there's more structure. It's also endowed with this aphanoid, K-aphanoid atlas. But in particular, we get something which is a locally ring space, which we obtain by gluing certain aphanoid Berkovich spaces along aphanoid subsets. And somehow what I'm trying to point out here is that the gluing data corresponds in a natural way to the dual graph. So the dual graph is telling you how to glue these things together. And here's a picture. If I have a model for a Tate curve that looks like this, then the corresponding dual graph is a circle, right? This edge corresponds to that singular point. This edge corresponds to that singular point. And there's two marked points on this graph corresponding to the two components. And then what I'm doing is I'm gluing two aphanoids, one which sort of looks like this, and one which looks like that, along their common intersections, which is, you can see, just this thing here and this thing here. And so this is trying to give you some idea of why the dual graph embeds inside of the space. So let me see if I can. You'll see one more slide that might be useful for understanding what's going on. But the reduction map pi on these level of rigid points extends naturally to k-valued points extends naturally to a map from the Berkovich space to the scheme Z, where the target is a space of all scheme theoretic points. And this is because you have all these new points of Berkovich space, these non-classical points, and they have to have somewhere to go under the reduction map. And if you actually allow your target to be all scheme theoretic points of Z, then they have somewhere to go. And there's a natural definition, which I won't give, of what this map is in terms of semi-norms. But the interesting feature of this map is that it's anti-continuous with respect to the Berkovich topology on X and the Zariski topology on Z. So the inverse image of an open set is closed, and the inverse image of a closed set is open. And for each irreducible component of the special fiber, there is a unique point of the Berkovich space which reduces to the generic point. Okay, so this reduction map is in this, well, these are all strict spaces. This reduction map is surjective, and over each generic point of each component, I have a single well-defined point of Berkovich space that reduces to it. And those were in the picture here. You saw there were these kind of two marked points. This point was corresponding to the generic point of Z1, and this point corresponds to the generic point of Z2. And those actually are marked points inside the Berkovich space, marked by this model. So here's this kind of retraction map. For each component, this space xi star, as you could see in that picture, it deformation retracts just onto this point zeta I. So it's a contractible space. And you can identify that point zeta I, that's coming from the vertex of the dual graph. And for each singular point P, this space xp deformation retracts onto a segment whose endpoints are zeta I and zeta j, and that's identified with an edge of the dual graph. And remember, this formal fiber was an annulus, and if you remember the structure of an open annulus from the pictures I drew, it has this kind of segment running between two boundary points and then a bunch of trees hanging off. So that segment is the edge. So the formal fiber contains this segment in it that's connecting these two Gauss-like points, zeta I and zeta j, together. And that's how you're embedding. The dual graph is embedded inside your Berkovich space. Somehow the edges are the vertices are coming from these points that lift the generic points of the irreducible components, and the edges are the spines, or the open edges are the, what was I calling it? The, sorry, I'm blanking on the name, but the, so I can't remember my own notation, sorry. So this segment, E sub p, you're supposed to think of as as linking the Gauss point of xi star, which is zeta I, to the Gauss point of xj star, which is zeta j. So if you globalize, the entire Berkovich space admits a deformation retraction onto this reduction graph. All right, so let me talk about the metric now. So I've sort of said what it is, but let me write this down. So h of x will be the complement of x of k inside of the Berkovich space. So these are kind of all the new points that you've thrown in, the Berkovich hyperbolic space associated to x. And since, it's not really hyperbolic anymore. Anyway, since the complement of these points zeta 1 through zeta t, this is actually a disjoint union of open sets which are isomorphic either to open disks or to open annuli. So at least away from these marked points, things locally look like subsets of the Berkovich projective line. So the idea is that since we've already metrized the Berkovich projective line, and away from these special points zeta 1 through zeta t, things look locally, analytically, like subsets of Berkovich projective line, we can just define a metric by saying that these should be isometries. So in particular, the most important construction is that if you have a double point P in the special fiber, and the formal fiber is some open annulus, then the length of that corresponding edge is the modulus of the annulus minus log, oh, well, I guess alpha was a real number before, so this probably should be alpha, not absolute value of alpha. But an open annulus has a well-defined modulus in p-adic analysis, just like in complex analysis, and it's actually the unique conformal invariant. So two open annuli are analytically isomorphic if and only if the modulus is the same. And because of that, you can show that this metric is canonical. So it doesn't depend on our choice of a semi-stable model. So in other words, well, let's see, I hope, do I have a picture? Well, in any case, in the Tate curve, those two, actually, in the Tate curve, the length of the circle turns out to be minus log absolute value q, where q is the uniformizing parameter. But you can also think of that in terms of the modulus of these open annuli. So the skeleton has, so let me define the skeleton. You see the set of points of Berkovich space which correspond to irreducible components in the special fiber of genus at least one. This is independent of the semi-stable model, roughly, because all you can do to get other semi-stable models, you can blow up certain points in the closed fiber. This introduces new P1s, but it doesn't introduce any new components of higher genus. So the components in some model of the special fiber of some model of genus bigger than 0, those are marked points of the Berkovich space. So I'll call them the marked points. And the set of marked points is empty if and only if X is a Mumford curve. These are the things that, if you remember from Jeremy's talk, can be p-adically uniformized by the p-adic upper half plane. So there are connections here between these various talks that, in other words, if all of these components in the special fiber are p1s intersecting transversely, that's some kind of totally degenerate reduction which can be p-adically uniformized. So in case you don't have a Mumford curve, you have some definite marked points. Now, if the genus of the generic fiber is at least 1, then there's actually a well-defined canonical subgraph, which I'll call sigma, Berkovich calls the skeleton, and it contains the set of marked points, and it has no vertices of degree 1. So if we had any edges that, so if we have any vertex of degree 1 in our tree, we can just kind of retract the edge containing that onto a smaller graph. And there will be some, so like you could have the circle and maybe a little tree hanging off it, and that tree has some vertices of degree 1. So that's somehow not minimal. The skeleton is kind of corresponding to a minimal model. So you can contract those trees and you get, there's a maximal subgraph which has no vertices of degree 1 and contains the marked points. And this is actually well defined. It's a canonical thing, and it's well defined as long as the genus is at least 1. When the genus is 0, you have no marked points, and well, you have no marked points, so you don't, I mean, you can, the whole space is contractible, but you don't sort of know where to contract it to. So in this case, there's nothing you can really do that's canonical. But otherwise, like in the Tate curve case, the whole space retracts onto this circle, and there's something canonical about that circle, something minimal about it. In fact, in the case where the genus is at least 1 and X is defined over a discretely valued field K0, then the skeleton is the dual graph associated to a minimal regular model. And in fact, you can think of the theory of I mean, it's very closely related to the theory of minimal regular models. The sort of non-existence of a unique minimal regular model for curves of genus 0 is related to the fact that there's no canonical skeleton. So somehow, I guess the thing I should have said is that when the genus of the generic fiber is at least 1, then either you have some marked points or you have a graph with some homology, because somehow the sum of the genus of all those marked points plus the genus of this graph is the genus of X. And so as long as the genus is at least 1, you either have a graph with some homology, which you can view as a canonical thing sitting inside your space, or you have some marked points. And then the whole space will retract onto the skeleton, is where I'm going to. So there's a canonical object that the entire Berkovich curve retracts onto, except in the case of genus 0, where you could pick any point, like the Gauss point, but it's not really canonical, and retract onto that. And as I mentioned, this is connected with non-Archimedean uniformization. So if E is an elliptic curve with multiplicative reduction, then the rigid space associated to E is a quotient of the rigid space associated to the multiplicative group by some multiplicative lattice. And you can view the Berkovich space as sort of taking a closed annulus and identifying these two kind of boundary annuli, really, but if you like, the boundary circles of this annulus, V1 and V2, and you take a closed annulus and the two boundary pieces you glue together. So if pi is this kind of topological quotient map, then it gives you an isometry with these metrics that I've been describing, and this closed segment of length minus log q, right? So the corresponding open annulus has modulus minus log q. And so you're taking this open annulus, which you remember the Berkovich picture was I had a segment and then lots of trees hanging off it. So you take that segment connecting the two ends of the open annulus and you just glue them together. That's what we're doing. So we're taking this segment of length minus log absolute value q, and we're gluing it together into a circle of that length. And so that's what's happening topologically with the Tate uniformization, is that you can just visually see the uniformization as wrapping a segment around to get a circle, and all those trees you had hanging off, of course, in that open annulus now are hanging off the circle. So that picture that I showed of a Tate curve is, you can really see why it's covered by P1 minus 2 points. In fact, the Berkovich projective line minus 0 and infinity, this is a universal covering space in the sense of topology of this Tate curve, and the covering group is Z. So somehow you can really see things topologically that in classical rigid analysis are just not possible. You can just sort of formally treat the Tate curve as if it has a fundamental group Z, but here it really does. And the Tate uniformization is actually a covering map. So it's a nice way to visualize things. All right, so now I want to bring in this theory of the Laplacian that I mentioned last time. So by having worked in this generality of arboreta, we have the advantage that now we have a Laplacian on a Berkovich curve. I just have to describe the arboretum structure. So we can look at continuous piecewise affine functions. I guess first I want to define harmonic functions, because this is how I structured the lectures. Was first I defined harmonic functions and subharmonic functions, and then I told you about the Laplacian. So the set of tangent directions is defined in exactly the same way as before. If U is a domain and I have a continuous extended real valued function, then I can say it's continuous piecewise affine if I'm just essentially recalling the definitions from before. When you restrict to this hyperbolic space, it's piecewise affine with respect to this path metric that I've now defined. And you have, at each point, the directional derivatives are 0 in all but finitely many directions. So it's just generalizing to curves the definition that I had before. And for such a function f, this quantity minus the sum of the slopes is well defined at every point that outside of the classical points. Right, again, the metric is infinite. These points of x of k are infinitely far away with this metric that I've defined. And so I don't really want to talk about directional derivatives there. And so if U is a domain, then I'll say that a function h is harmonic, a real valued function h is harmonic on U if it's continuous piecewise affine and it's harmonic at every point inside, meaning either the sum of the slopes is 0 or you have a type 1 point and the function is locally constant at x. And so here's a theorem. If f is a non-zero meromorphic function on my curve x, and capital F is the unique continuous map which extends this valuation function minus log absolute value of little f, then capital F is actually continuous piecewise affine, and it's harmonic outside the zeros and poles. So again, exactly what you would expect by analogy with the classical case over the complex numbers, that outside the zeros and poles, this analytic function little f, when you take minus log absolute value, you get something harmonic. And what I want to do is explain what this actually means at these marked points, zeta I, because this actually is saying something interesting. And in fact, that's really the only place where it's saying something that we don't already know, because, as I mentioned, every point other than these marked points kind of locally looks like, has a neighborhood which is a simple domain in P1. And by some functoriality principles, since we know this corresponding result on P1, to show that this function capital F is harmonic, it suffices to check it just at these marked points zeta I, which really don't have neighborhoods that we already understand. So what I want to do is tell you what the tangent space at such a point means. Remember, zeta I corresponds to the generic point of a component of Z, of my special fiber. And so I claim there's an interpretation of these directional derivatives. They actually have some meaning in terms of the theory of schemes. So let's see why this function is harmonic. All right, so in order to do that, I want to describe the tangent space. So at this point zeta I, think of it as sort of the like the Gauss point. It corresponds to some model. If you take this sort of standard model proj of k, x, y of P1, this has good reduction. There's one component in the special fiber, and the unique point mapping to that under the reduction map is the Gauss point. So that's why I'm saying that these zeta i's are like the Gauss point. They really do, in some sense, generalize that notion. And the point is that the tangent space, the tangent space is naturally in bijection with the set of closed points of the special fiber on this component. So the closed points of this component Zi are in one-to-one correspondence with the tangent space. And this is, you're supposed to think, at the tangent space at the Gauss point, those were the different residue classes, right? Or in other words, the open disks of radius 1, or the closed points, P1 over the residue field, right? The tangent directions at the Gauss point in P1 corresponded to P1 of the residue field. So here, at the point zeta I, the different tangent directions correspond to the closed points of Zi. And so I'll make this bijection explicit by writing V of Z for this kind of formal unit tangent vector emanating from the point Zi in the direction corresponding to a point on the special fiber, corresponding to a point on this component Zi. And so now we want to interpret these directional derivatives. So for each component Zi, there's some non-zero scalar Ci, so that Ci inverse f reduces to a non-zero rational function. So the content here is just this. I want to sort of be able to take my meromorphic function f and kind of reduce it and see what it gives me on the special fiber. But that might not make sense, right? Because I might have to rescale. If you want to just think in terms of coordinates, I might have to rescale things so that the reduction is actually a well-defined non-zero rational function. And there's kind of a unique way to scale this. At least, well, Ci is not uniquely determined, but the absolute value of Ci is well determined. And then the divisor of what you get on Zi is well defined. So if I look, I take this suitably rescaled version of f and I specialize. I reduce it modulo the maximal ideal, and now I can look at the zeros and poles of that thing on the component Zi, and this actually makes sense. So you can define the order of a rational function f at a point of the special fiber to be the order of vanishing of this reduced rational function once you've rescaled. And so here's the results of Bosch and Lütke-Bomert. So in this context, if f is a non-zero meromorphic function on x and little z is a point of the special fiber, then for each component, for each I, this directional derivative is just the order of vanishing. So the derivative in the direction of that closed point z of the function log absolute value f is just the order of vanishing of f at that point on the closed fiber. So this directional derivative is just encoding the order of vanishing. And I think I got the sign right here, that it is actually plus. But I kept getting confused about that. So since a rational function on a complete non-singular curve has the same number of zeros as poles counting multiplicities, what does this tell you? It tells you that if I take the Laplacian at this point zeta I of minus log absolute value f now, that's the sum over all closed points of zi of the derivatives of this function in all those different directions, right? It's the sum of the slopes in all directions. The directions correspond to points of the closed fiber. And by what I just told you, that's just the sum over all points of this component zi, over all closed points of zi, of the order of vanishing of f at that point. But zi is a complete curve, so that's 0. So the fact that this function, minus log absolute value f, is harmonic at this point zeta I ultimately rests on this interpretation of the directional derivatives as orders of vanishing, and the fact that on each irreducible component of the special fiber, number of zeros equals the number of poles with multiplicity. And so this is related to this valuation polygon stuff that I was telling you about before. It's somehow more geometric, more conceptual interpretation in terms of the theory of schemes. And so anyway, this explains why this function is harmonic at these special points zeta I. Okay? Now, the arboretum structure comes from semi-stable models. So if I have a semi-stable model script x for my curve, its dual graph, as I've said, has the structure of a metrized graph. And given any two semi-stable models, this was mentioned in the formal context in terms of Raynaud's admissible formal models before, there's some third semi-stable model which dominates both of them. But I'm just talking about curves right now. So this can be made quite explicit using blow-ups. And so consequently, what you find is that this collection of all dual graphs of semi-stable models of your curve forms an arboreal system of metrized graphs in the sense of the previous lecture. And theorem, this makes X Berk into an arboretum in the sense that as a topological space, it's homeomorphic to this inverse limit. So this also tells you sort of how to visualize the topology on these spaces that, picture it as a graph with all these trees hanging off it. It's the inverse limit topology coming from all these finite subgraphs. And so now we have a Laplacian operator because I already told you that on any arboretum you have a natural way to define a Laplacian. So we can ask, for example, for an analog of the Poincaré-Lalonde formula, which I had stated for P1, and this is proved in Touillet's thesis, among many other things. And it just says that the Laplacian of minus log absolute value f is a bunch of point masses supported at the zeros and poles of f with the correct multiplicities. Sorry for using capital F and little f. That was stupid. So anyway, what I told you before is that this function was harmonic outside the zeros and poles. And now I'm saying something more precise, that the Laplacian is actually 0 outside the zeros and poles, which does mean harmonic, but at the zeros and poles, it picks up the multiplicities. And so this is some kind of generalization of the theory of valuation or Newton polygons to the case of general curves, if you want to think about it that way. So maybe, let's see, just as a quick example, the canonical distance, which I mentioned before, this minus log, actually I guess I didn't define it relative to an arbitrary point z. Never mind, let me skip this. I didn't define that. But, oh, I'm sorry, no, I am defining it here. I remember what I'm doing. If I pick any 2 points y and z, then up to a constant, there's a unique function, x, y sub z, so that minus log absolute value, minus log of this thing satisfies this differential equation. So in other words, I'm just defining this generalized canonical distance here before I defined it for z equals infinity. But I'm telling you, you can define it in general as just the unique solution to this differential equation, unique up to some constant. And so this gives you a convenient way to generalize certain constructions just by solving a differential equation. So this we'll call a canonical distance function relative to z. And possibly non-obviously generalizes the canonical distance, which was introduced in the first lecture, which was itself just an extension of the absolute value of x minus y. So in fact, what you can do with this canonical distance is you can factorize absolute values of meromorphic functions. If I have a meromorphic function f, whose divisor is the sum of mi ai, then just pick any z at all that you like, and the absolute value of f at any point of Berkovich space just factors as the product of these things. So it's like you can just treat a general meromorphic function on a curve as if it were just a rational function on P1, in the sense that you're just writing it as a product of these things. It looks like sort of one polynomial over the other. The mi's can be positive or negative. So it's some kind of primitive function that allows you to factorize absolute values of meromorphic functions. But it's less easy to write down explicitly than it is in the case of P1, where you can just take the absolute value of x minus y. But this kind of thing works for general curves, and seems to me the best way to understand this. I mean, why is this true? You just take the Laplacian of both sides, and you see that they agree by the Poincaré-Lalonde formula. So it's a very simple result once you have that theory. So the last thing that I want to do is just to mention an application of this. I haven't really discussed applications. And again, like in Brian's case, this is not the most serious application of this kind of stuff. I mean, Berkovich's theory has many, many very amazing applications. Here's one application that got me interested, though. If you have the Berkovich analytic space associated to an elliptic curve, and I have this skeleton sigma, which is either a point in the good reduction case or a circle of this length in the multiplicative reduction case, and I want to say that the local height function on the elliptic curve has some kind of interpretation in terms of Berkovich spaces. So, okay, something about, in the good reduction case, it's related to narrow models. Let me skip that because I'm running out of time. There's a canonical probability measure on this Berkovich space, namely a point mass at this Gauss point in the good reduction case, and Haar measure on the skeleton in the bad reduction case. So you just take the uniform measure on the circle or a point mass at that point, depending on which case you're in. And I claim that this standard local canonical height function, which I'll pretend you know what that means, and I'll call it lambda, it extends naturally to Berkovich space, which isn't surprising because these things are defined as limits of things of the form log absolute value something, and by definition such things extend to Berkovich space. So it's natural to expect these kind of functions to make sense on Berkovich space. And it's singular only at the origin. And here's how to characterize it. This local height is the unique function which satisfies this differential equation. Its Laplacian is a point mass at the origin minus this measure mu. And this works in the good and bad reduction cases. And, well, it's unique if I require that the integral of this local height function against this measure mu is 0. And actually, the standard normalization given in Silverman's book by some explicit formulas actually has this nice property that the integral against mu is 0. And that you can see why this is the right normalization and why this is canonical. And there's something very analogous to this in the complex case. So it really kind of unifies the theory of local heights. They all are the unique solutions to an equation just like this. So it's kind of a Green's function, just as in the Archimedean case. And with the appropriate definitions, which I don't have time to give, you could say that this local height is subharmonic outside the origin and superharmonic outside the skeleton. And there's a maximum modulus principle, et cetera, so you can say various things about what this local height looks like using that. But the thing I want to mention, and this is the next to last slide, I think, is a global application. And just very quickly, here's what it is. You have a global Néron-Tate height over a number field, which is a sum of local heights. And you can use this interpretation I gave to actually prove something. So at every place you have a Berkovich analytic space associated to V, which you take to be the usual complex torus in the Archimedean case, but you take the Berkovich space in the non-Archimedean case. So at each place you have some Berkovich space. And at each place, you therefore have a canonical probability measure. Haar measure on this complex torus in the Archimedean case, this point mass in the good reduction case, and Haar measure on this circle in the multiplicative reduction case. And the global height is a sum of these local heights which satisfy the differential equations with respect to these measures. And so what one can prove is the following adelic version of the Spiro-Ulmo-Zhang equidistribution theorem, which is the following. So this is due, depending on how exactly you state it, to Spiro-Ulmo-Zhang in the Archimedean case, Chambord-Loire in the good reduction and partially in bad reduction case, and Peche and I have a proof using potential theory in the non-Archimedean case. And it just says that if K is a number field and E is an elliptic curve, you fix a place V, you fix an embedding of E of K bar into the corresponding Berkovich space, take any sequence of points over K bar whose heights go to 0, take the probability measure supported equally on the Galois conjugates of those points. Then those point masses converge weakly to this canonical measure. And this works uniformly at all places V, and the proof is the same at all places V. So there's a nice way to do this simultaneously. And so you can prove this using Arakelov theory as developed by Chambord-Loire, or in a more elementary way, using the following principle. This is the very last thing on the last slide. So here's something that uses the theory of harmonic and subharmonic functions. This measure, mu v, has a certain minimization property. If I define this functional on the space of probability measures on my Berkovich space, I just integrate the local height function d nu of x, d nu of y. Then this measure mu is the measure of minimum energy. That's the property that it has. So you have equality. Every measure has energy bigger than the canonical one, and you have equality if and only if nu equals mu. And this you can use to prove such equidistribution theorems, because if I have this sequence of Galois orbits, these measures supported on Galois orbits of points, and I want to show it's converging to this canonical measure, I just have to show it minimizes energy. And this can be done by relating the energy to the global canonical height. So this is some kind of application of this theory to arithmetic. And I'll stop there. Thanks. Yeah, so the question is, if you have a finite map between curves, does it take the skeleton to the skeleton, and what can you say? Actually, Antoine Ducrot is the expert on this, so he's written papers on this subject. So it's true not only for curves, but in general. What's that? The question was, if you have a finite map between curves, does it take the skeleton to the skeleton, and what else can you say about what's happening topologically? So. Okay, so yes, so see Antoine's paper. Question? Is there a way to think about non-singular? Singular curves. Is there a way to think about singular curves in the Berkovich setting? Well, the construction makes sense. In terms of drawing the kind of picture or applying the same kind of semi-stable reduction theorems, I guess it's more subtle. I don't have a good answer other than that the construction of the space certainly makes sense, but it's possibly more subtle to analyze what's going on. And I'm sure that various of the things I've said about piecewise linear functions, meromorphic functions inducing piecewise linear maps, and the harmonic functions and all that is much more delicate in the singular case. Yeah, you can have models that just have two components meeting at one point.
So what does the skeleton look like then?
Well, you have two vertices for those two components and one edge between them. So it's
That the skeleton didn't have vertices of one.
no. Well, the yeah. So right. I have to. Yeah. So at the moment. I was trying to simplify some definitions in this context, and I seem to maybe have done it wrong. So in that case, yeah, I think maybe I want to say that the unmarked points have are supposed to have vertex, or not. You don't have any unmarked points of vertex 1. Yeah, I was clearly not including this kind of case in. Yeah, so I apologize for that. There's a very general definition of the skeleton in Berkovich, which applies in higher dimensions as well. And it's a more, you have to say, you have to be more careful in order to define it. So I was trying to simplify the definition in this case.